everybody. In this video, we're going to talk about the savings annuities formula and where it comes from. So take 3 deep breaths and let's make this math easy. So this is what the savings annuities formula looks like. And let's go through and talk about what the variables mean. So just like all of our other formulas so far, A is going to be the total amount that you end up with in your savings account by the end. R is the annual interest rate. K is the number of compounds per year. And this new variable D represents how much money you're depositing in each compound period. So for the most part, in all of the homework assignments you're going to be doing, we're going to be doing monthly compounding, and you're also going to be making monthly deposits. So the number of compounds needs to match how often you're depositing the money. And then just like before, T is going to represent the number of years. And the reason why this formula is so complicated is because you're earning interest on the money that you're investing, but you're not investing all the money all at once. You're investing the money in monthly deposits. And if you're doing that, then like the money you invest in the first month is going to make much more interest than the money you invest like 3 years later, because there were 3 years where it wasn't earning interest. And so that's why the savings annuities formula looks kind of complicated like this. So when you're simplifying the savings annuities formula, make sure that you follow order of operations. Because remember, order of operations says to simplify everything inside of the parentheses, and then you can do multiplication and division and stuff from there. So when you're calculating this formula, you want to start with your innermost set of parentheses. Although you can also simplify the exponent like we've been doing in the compound interest formula. And then you'll take that number and subtract 1. And then once you're done with that, then you can multiply by D and divide by this fraction. So always work from your innermost set of parentheses and work outwards from there. So for the rest of this video, I'm going to show you where the formula comes from. But if you don't really care about where the formula comes from and you're fine just using it, you're welcome to skip the rest of this video. But I think it's kind of interesting to know where the formula comes from. So if you want to, you can watch the rest of the video to see that. So let's say that we had a savings account that had an annual interest rate of 6%, and we were making a monthly deposit of $45. So the first thing to know is that the compounding period needs to match the deposit period. And so because we're depositing money every month, our compounding period is also going to be every month. So our monthly interest rate can be calculated as 0.005 because that's 6% divided by 12. And then just like in our compound interest formula, you're going to add a 1 to that because you keep 100% of all the money you've invested so far. So if we start off with an amount of 0, so I'm going to use these little subscripts to let us know which month we're on. So on month 0, we haven't invested any money at all, and so we have $0. After 1 month, we're going to have 1.005 times the amount of money we had from the last month, which in this case is just going to be 0 because we had $0 last month. But I'm going to charge interest on however much money is in my savings account from the month before. And then I'm going to add $45 because I make a deposit. So after 1 month, I have $45. Then for my second month, I'm going to calculate interest on the money that was in the account from the month before. So the month before, I had $45. So I'm going to put $45 in for that amount. And I get 45 times 1.005, and then I also add in my monthly deposit for that month. Then in month 3, I'm basically going to do the same thing. And I'm going to take last month's amount that I have and charge interest on that, and then add a deposit. And when you simplify that all out and distribute it, you end up with this expression for the amount of money you have on month 3. Then you'll do the same thing for month 4, and so on and so forth, for however many months you decide to save this amount of money. And if you look at the calculation for month 4, you might notice that there's a pattern in there, because you basically have 45 times your interest percentage, and you have decreasing exponents on these terms. And so after m months, we basically will have 45 times our interest percentage raised to the number of months minus 1. Because when we were at 4 months, we had a largest exponent of 3. And so after m months, we're going to have a largest exponent of m minus 1. And then that's going to decrease all the way down until you just have a 45 that's not multiplied by anything. And so this equation tells us how much money we're going to have at month m. But it's a rather complicated equation because it's super, super long and there's lots of exponents and lots of things in it. So the idea is we want to simplify this and see if there's an easier way to write it. And so the way that we do that is we say, okay, well, it's kind of weird that this is like an m minus 1, but if I multiplied by this decimal one more time on both sides of the equation, then this exponent would go up to m because I'd be multiplying by this an additional time, and so the minus 1 wouldn't be necessary. And so I'm going to multiply both sides of the equation by 1.005, and that basically makes all of these exponents go up by 1. Then I'm also going to multiply this equation, the entire equation, by a negative, and that gives me this result. And the reason why this is useful is because if we add these two equations together, almost everything in the equation ends up canceling out. And the only thing we're left with is 0.005 times that total monthly amount we have at the end of month m. And that's going to equal 45 times 1.005 raised to the m power minus 45, because all of the complicated terms in the middle all ended up canceling each other out when we added these two equations together. And if we take that equation, we can notice that there's a 45 in both of these terms. So we could factor the 45 out, and that gives us this expression inside of parentheses. And then to get this variable by itself, we could divide both sides by this decimal, which tells us that the amount of money at the end of month m is going to be this expression here. So this equation describes a specific situation where we have a monthly deposit of $45 and an interest rate of 6%. But we could generalize this to get the general equation, because this 0.005 came from taking our interest rate and dividing it up into groups of 12. And in general, we could replace that with our interest rate divided by the compounding period. Same thing with this 0.005. We could also replace that with this fraction. And then the 45 was our monthly deposit, and so we could replace that with a variable D, and that would end up giving us our savings annuities formula. So that's where the formula comes from.